Back in early 2020, the global pandemic wreaked havoc on global supply chains, leading to significant disruption in production and delivery of electronic components. Demand for electronics soared as people worked from home, further straining the already limited supply. So companies struggled to secure the necessary materials and parts, impacting innovation and development across the entire industry, as well as a bunch of other industries that it touched. Fast forward to today, we've transitioned from a period of scarcity to surplus. Now, while this might seem like a positive development, the industry still faces numerous materials challenges. The geopolitical climate, including tensions and in some cases all-out war between major players in the industry, continues to impact the global supply chain. And additionally, the shift in manufacturing to Asia, particularly Taiwan and Korea, creates a dependency that has proven to be problematic. So to ensure long-term stability and support future technological advancements, we have to focus on developing sustainable materials solutions. So today, let's explore 5 ways we can strengthen the electronics materials industry so that unexpected disruptions are kept to an absolute minimum. That's what we're talking about today. My name is Joel, this is Octopart. Let's gear up and dive in. The global pandemic shook the world in many ways, but one of the less obvious impacts was on the electronics supply chain. Electronics became even more critical to our lives during lockdown, but just when we needed these devices the most, the supply chains that produced them faced major disruptions. Now, many electronic components are manufactured in China, which was the first country to implement strict lockdowns to control the virus. Factories shut down, and the production of essential parts for electronics slowed significantly. Now, this wasn't the first time a health crisis had disrupted the electronic supply chain. Similar situation occurred during the SARS outbreak in 2003-2004. Electronics rely on a wide range of materials, many of which are mined in different parts of the world. For example, cobalt, which is crucial for lithium-ion batteries, mainly comes from the Democratic Republic of the Congo. Other key materials like rare earth elements used in magnets and displays are often sourced from countries with complex geopolitical landscapes. The pandemic really highlighted how vulnerable these individual supply chains are to disruptions. Now, the extraction and processing of materials for electronics also raises environmental and social concerns. Mining activities can have significant ecological impacts, and there are often social issues related to labor conditions in mining regions. Companies are increasingly aware of these risks, which can affect their brand reputation and long-term sustainability. So in response to the issues uncovered by the pandemic, many companies implemented bold new strategies to diversify the ways they got their electronics materials. We've also seen huge shifts in the geopolitical landscape since then, some of which impact the industry's largest producers, as well as significant investments from up-and-coming players in Latin America, Europe, Southeast Asia, just to name a few. And while these strategies, along with stockpiling, better supply chain management in general, nearshoring, onshoring, and more, have helped to get the global electronics industry from shortfall to surplus, there's a new layer to this game that's complicating the way forward. In the post-pandemic world, the shift toward clean energy has drastically accelerated due to a variety of public and private incentives the world over, as well as the escalating consequences of global climate change. Now, one of the biggest hurdles in this transition is acquiring the necessary minerals and rare earth elements to power this new tech. These critical materials are vital for producing clean energy technologies, but there's a significant supply-demand gap that poses a threat to the energy transition. Here's a closer look at these challenges and the impact on electronics materials. The energy transition relies heavily on minerals like lithium, cobalt, copper, nickel, and rare earth metals. Now, these elements are crucial for manufacturing electric vehicles, renewable energy systems, power grids, you name it, all kinds of clean energy technologies. However, there is a substantial gap between the supply of these minerals and the rapidly growing demand. According to recent data, resource extraction has surged by nearly 400% since 1970, and it's expected to increase by another 60% by 2060. So the adoption of low-carbon technologies needs to skyrocket to meet these climate goals and meet the demand, but these technologies are much more material intensive than their conventional counterparts. This means we need a massive ramp up in the supply of critical materials at a pace unprecedented in all of human history. One major issue is the time it takes to expand mining operations. Now, the process of permitting, exploration, asset development, all this can take decades before production even begins. And despite policies like the Inflation Reduction Act, which aims to boost investment and reduce supply constraints, the pace of development is still really slow. As a result, many critical materials are expected to face a supply-demand imbalance by 2030, even under optimistic scenarios. So the failure to meet this demand has some serious economic and environmental consequences. For instance, some estimate that failing to meet the mineral demand could result in an additional 400 to 600 million tons of CO2 emissions by 2030, and that is exactly what we are trying to avoid. This imbalance is already sparking a global race for resources among countries, and as you can imagine, that is raising geopolitical tensions the world over. The Security Minerals for Energy Transition initiative by the World Economic Forum has identified several risks associated with this supply-demand gap. They include, number one, economic risks. Shortages of raw materials could drive up prices for clean energy technologies, which makes them less affordable. Number two, environmental risks. Delays in the energy transition could hinder progress in addressing climate change, as there won't be enough technologies to support the transition that we need. Number three, social risks. Without responsible mining practices, there could be negative impacts on communities and the environment. Meeting ESG, or environmental, social, and governance standards, is absolutely crucial in this regard. Number four, political risks. Rising costs due to material shortages could reduce political will to support the energy transition that we need. Additionally, countries may intensify efforts to control critical mineral supply chains in this kind of environment. So what's to be done to address these current and oncoming electronics materials challenges? Well, let's go to our 5 solutions to these materials issues. Hi there, Joel here. You have made it pretty far in this video, which is completely awesome. We put a lot of care and consideration into these things, so we are thrilled that you're enjoying them. But before we get to our 5 solutions, would you kindly take a second, just do any combination of liking the video, subscribing to the channel, leaving a comment with your thoughts. It helps keep us going, costs you nothing but a moment. All good? Okay, I appreciate you. Back to the video. One of the most promising solutions is to shift towards sustainable materials. Now, the electronics industry heavily relies on non-renewable resources, which isn't great for the environment. But by using renewable plant-based sources and controlled microbial bioreactors to create plastics, we can reduce our dependency on fossil fuels significantly. This move not only helps the environment, but also secures a steady supply of materials for future electronics. Good news here, there's already been significant advancement in developing renewable plastics. Researchers are currently exploring ways to create biodegradable and plant-based plastics that can be used in various electronic components, from circuit boards to casing materials. However, scaling these productions for mass production really is where most of the challenge is these days. It's crucial to continue investing in research and development for making these sustainable materials viable and cost-effective so that we can see them in widespread circulation. Toxic substances in electronics pose a significant challenge, but thanks to regulations like the EU's RoHS directive, we've seen a reduction in harmful materials like lead, cadmium, and hexavalent chromium. However, finding non-toxic alternatives for flame retardants and other hazardous substances remains pretty difficult. Continued research and development in this area could lead to safer, more sustainable materials for electronic components. Flame retardants are actually a prime example of the challenges faced in reducing toxic substances. Now, while they play a critical role in preventing fires, many traditional flame retardants are harmful to the environment and to human health. Researchers are currently working on developing new, less toxic flame retardants that can provide the same level of protection without all the negative side effects. Innovations such as bio-based flame retardants, which are derived from natural sources, really show some promise in this area, but we got a long way to go before we see this become industry standard stuff. Making electronics more energy efficient not only saves power, but also reduces the strain on resources used to produce the energy. Many manufacturers are already doing a great job here with innovations that reduce electricity consumption, but we can go further by optimizing server facilities and promoting energy efficient designs in all electronic devices. This will help cut down on the overall environmental impact and preserve the resources that we're trying to protect here. Energy efficiency labels and standards play a crucial role in promoting energy-efficient products. So programs like Energy Star, for example, help consumers identify electronics that meet stringent energy efficiency criteria. By adopting and adhering to these standards, manufacturers can drive innovation in energy-saving technologies. Additionally, encouraging the development of ultra-low power electronics can lead to significant energy savings over the life cycle of the product. Dematerialization is all about doing more with less. By using advanced software and CAD systems, engineers can design electronics that use fewer materials without compromising functionality. So this includes shrinking the size of devices and replacing hardware with software solutions. And these innovations not only save materials, but they also reduce the weight and environmental footprint of electronic products. Generative design is a cutting-edge technology that uses algorithms to create optimized designs with minimal material use. And engineers input specific criteria such as weight, strength, material type, and the software generates multiple design options that meet those requirements. This process not only reduces material consumption, but can also result in innovative designs that were previously impossible to create. As generative design technology advances, it'll play a pivotal role in dematerializing electronic products. Recycling is key to ensure a steady supply of materials like metals. Currently, many valuable metals such as copper, silver, gold are successfully recycled and reused. However, recycling needs to expand to include more complex components like thin films on semiconductor chips and rare metals like gallium and indium. By enhancing our recycling technologies and practices, we can recover more materials and reduce the need for new mining operations in the first place. One exciting area of development here is the use of advanced recycling technologies that can separate and recover rare metals more efficiently. For example, hydrometallurgical processes use liquid solvents to extract metals from electronic waste. This method is more environmentally friendly and can recover a higher percentage of valuable materials compared to traditional smelting processes. Investing in these technologies and ones like it will be crucial for meeting future material demands. Recycling is, to me, the most exciting of these 5 tactics because when you allow yourself to get a little speculative, the numbers really do get astounding. So let's step into our speculation machine for a moment and dream big on electronics materials recycling. Currently, only about 15 to 20% of e-waste is recycled globally. With improved recycling technologies and practices, this rate could be significantly increased with not a ton of effort. Now, electronics contain various metals, some of which we've already talked about today, including things like copper, silver, gold, aluminum, steel, lead, stuff like that. So let's take these and consider the potential improvements in recycling with just these metals. So aluminum and steel are commonly recycled metals, but with improved practices, recycling rates for these could approach the 90 to 95% mark. Lead, particularly in batteries, is already highly recyclable. Improved practices could ensure that almost all lead that we use is recovered and reused. Now let's speculate on what these improved recycling practices might actually result in. Let's begin by considering the average metal content in e-waste. Here is a rough breakdown. In copper, you got about 20% of e-waste by weight. Silver, you got about 0.2%. Gold is 0.05%. Aluminum is around 5%. Steel is about 10%. And lead is about 1%. Now, as of some recent estimates, the world generates approximately 50 million metric tons of e-waste annually. With enhanced recycling practices, let's assume that we can increase the recycling rate to 80% of global e-waste. This would mean recycling 40 million metric tons of e-waste annually. So here's the breakdown of what that would result in terms of potential material recovery. Copper, 20% of 40 million metric tons, 8 million metric tons. Silver, 0.2% of 40 million metric tons, 80,000 metric tons. Gold, 0.05% of 40 million metric tons, 20,000 metric tons. Aluminum, 5% of 40 million metric tons, 2 million metric tons. Steel, 10% of 40 million metric tons, 4 million metric tons, and lead, 1% of 40 million metric tons comes out to 400,000 metric tons. So, by improving recycling practices, we could potentially recover 8 million metric tons of copper, 80,000 metric tons of silver, 20,000 metric tons of gold, 2 million metric tons of aluminum, 4 million metric tons of steel, or 400,000 1,000 metric tons of lead. Now, I have thrown a lot of numbers at you right now, and I don't want to keep going on that front, but let me just zero in on one of these. That's 33% of the annual global mined copper production provided in this one step alone, to say nothing of all the other metals that I just talked about. And that's just one of the steps on this list. Imagine what we could accomplish if we really zeroed down on recycling, plus some of the other stuff that I've mentioned in this video today. Again, these numbers are speculative, but if you check out the sources in the description, do a little bit of your own research, you'll see that it's not that speculative. Now, despite the challenges outlined in this video, there are many encouraging signs that the electronics industry is moving in the right direction. Collaborations between industry leaders, governments, and environmental organizations are driving forward sustainable practices and innovative solutions. For instance, initiatives like the Circular Electronics Partnership aim to create a circular economy for electronics where products are designed for longevity, repairability, and recyclability. These efforts demonstrate a collective commitment to sustainability and provide a roadmap for other industries to follow. And you, dear consumer, also play a vital role in driving sustainability in the electronics industry. By making informed choices and supporting companies that prioritize eco-friendly practices, consumers create a demand for sustainable electronics products. Educational campaigns, transparent labeling, this helps consumers understand the environmental impact of their electronics, the ones that they purchase, and this encourages more responsible purchasing decisions, which trickles all the way down to how we get the materials and what materials we get in the first place. So I think we've done a pretty good job here today of outlining the various challenges we've got going on in the electronics materials space. But materials aren't the only challenge ahead for the electronics industry. Did you know, for instance, that the United States electronics manufacturing industry is facing a workforce shortage and that there are going to be literally thousands and thousands and thousands of untaken jobs in this very country? If you want to learn more about that, check out this video. Got a big old deep dive on that topic. My name has been Joel. This has been Akbar. Thanks so much for watching. I'll see you in the next video.